Okay, so today's lesson, as I stated, is on buffers. All right, hopefully we've got that title down in all of the chaos of me talking here. And a quick definition of what a buffer is. Let me get rid of some of these boxes here. There we go. A buffer is actually an example of the common ion effect. I will review what the common ion effect is as I explain the buffer. Copying a slide doesn't make a good movie. But oh well. Everything we've dealt with so far in this particular course, this particular unit, dealing with acids and bases, and more specifically dealing with weak acids and weak bases, have been using the acid or base all on its own. I often say that it's in pure water. I'm going to redefine that in a moment, what I mean by pure water, just to kind of clear things up. And so we've had shortcut equations that allow us to calculate the H3O plus or the OH minus if these weak acids or bases, or conjugate acids and conjugate bases, are in that pure water. A buffer is a solution that contains a weak acid and then its conjugate base as well in the solution. Again, we have a common ion situation. If I have some HF, put it into solution, and I dissolve in it some sodium fluoride, I'm going to have some F minus in that solution. That's the common ion. That's how it's like the common ion effect. But in the end, the sodium I don't care about. It's a spectator. And so I'm going to have HF, the weak acid, and F minus, the conjugate base, in the solution. Both of them at the same time. If I were to use the same terminology I've been using in the past, I would say that this is not pure water. And so now I'm going to kind of change it. When I say pure water, I mean there's no common ions in there. In a buffer, there is a common ion. There is the conjugate base ion, or conjugate acid. I could also have a weak base, NH3, with its conjugate acid. In this case, NH4Cl, Cl being the spectator. And so in this solution, I'd have some NH3 and some NH4 plus. Both of them moderately weak acids and the moderately weak conjugate base, and vice versa. How does that allow a buffer to work? Well, if some strong acid was then added to a mixture, let's say of this first one, HF and NaF, if some strong acid is added to it, the whole area is going to be flooded with H pluses or H3O pluses. With this strong acid flooding everything, the conjugate base, the F minus, can react with it and neutralize it, thus buffering the effect of putting in that strong acid. If some strong base was added to a solution of HF and F minus, then there would be a flooding of OH in the solution, and the weak acid can donate its proton and neutralize the base that's added, again buffering the effect of the addition of the acid or base. So because in a buffer we've got a weak acid and a weak conjugate base, or vice versa, you can add some strong acid or some strong base, and those various components will take care of both. That's why it's called a buffer. It can grab it up and neutralize it so it doesn't affect the solution. A buffer solution resists a large change in pH when a moderate amount of acid or base is added to it. All right, So let's get to some calculations. This is the way it kind of works. So let's say we're dealing with this HF, F minus buffer. And I just want to stress the difference between if there's no buffer and then if we create a buffer. In this case, I'm saying no buffer. That's why I've got the title no buffer. And this is essentially what I would call a pure water scenario. And by pure water, I don't really mean pure. It can have other things in it, but it can't have this. What is the thing I'm excluding if I'm saying it's pure? It can't have this. Yep. Which in this case would be a common ion. F minus ions. I don't care if there's sodium. I don't care if there's potassium in there. I don't care if there's spectators. When I say pure water, I mean no common ion. That's what I really mean when I say pure water, that there's no common ion to mess this up. Now, we've already done all the work if there's no common ion. We had the ice table, and we don't count the water, and we start with the initial concentration of HF. We call that HF an initial or HA initial, 0, 0. We went through the whole motion, minus X, 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 a little bit of a review, etc., etc. And there was a way for me to get the H3O plus, which, by the way, is equal to the X for those of us who don't go back and review our notes. What is the formula for getting H3O plus in a weak acid scenario in pure water? Yep. Over the initial HF concentration, which we can get. This is a review. We know how to do this. Let's go ahead and do that. I do need the Ka, if somebody has the paper nearby. HF. 3.5 times 10 to the negative 4. This is 0.20 molar. Square root. That's going to get me H3O plus. Do not clear your calculator and get me eventually the pH. And that's not here, so we need some calculator people to step up. And we'll take the numbers when you get them. Yep, Eric? 10 to the negative 3, molarity, moles per liter, and negative log answer equals. What's that? Oh, error 1, yep. 2.1, one more decimal? 2.07, there you go. Okay? We know how to do that. We've been doing that calculation forever. That's really the only calculation we've been doing in this particular unit so far. Because it's either been a weak acid or a weak base. We've been using the pH calculations. It's always been pure water, no common ion, up to this point. All right? Let's now take a look at what happens when we add the common ion. Then we're going to add some acid and base to mess with the buffer. So next, we're going to talk about, and I'll just jump ahead, don't write this down yet, let's determine the pH of the buffer. But first, let's back up and let's create a shortcut, because there's a shortcut way of doing this. Again, I'm going to be dealing with, I'm going to just write this time HA plus H2O to produce H3O plus, and that is going to be plus A minus. So this particular scenario is actually an acid conjugate base buffer. All right, there's going to be two types. there's a base conjugate acid buffer, and then there's an acid conjugate base buffer. How do you know which is which? Well, the Ka for the acid is going to be bigger than the Ka for the conjugate base. That's what makes it an acid conjugate base buffer. If the Kb is bigger for the base than it is for the conjugate acid, that makes it a base conjugate acid buffer. Whichever one's the strongest out of the two pair, right? Remember, it cuts across the middle. In this case, the H, if we're talking about HF, HF is 10 to the minus 4. That makes the F minus like 10 to the minus 10, which means the HF is the stronger, and that makes it an acid conjugate base buffer, okay? The larger Ka versus its conjugate base, all right? If we're doing the calculation to determine the pH, I eventually need X, right? Because in the acid-base unit, X is either H3O plus or OH minus. All right, so let's write our stuff down. Ice, this time again, I've got HA initial, what we started with. The water doesn't count. I've got 0 H3O plus, and the fact that this is a buffer, or however you want to word this, because it's a buffer, I'm now going to also have a minus initial. That comes from the other ion. That comes from the other substance. That's what makes it a buffer. Now we're going to analyze it exactly the same way. I'm going to have minus X, X, X. I'm going to have HAI minus X, X, AI plus X. And I'm hoping that you could go through and solve this at this point. Be aware I might make you derive this as well on the test. You got the possibility of some derivations. And Ka, because this is the bigger Ka for the acid, it's an acid conjugate base, is going to be equal to X, and that's going to be times concentration of conjugate base, which is an A minus, right? And that's plus X, and then concentration of HA initial minus X. All right. This is looking like it could be a quadratic, but we want to avoid that, so what do we use? What do I do if I want to avoid the quadratic? Yeah. I can check the approximation. This is not a perfect square. Again, we're dealing with weak bases and weak acids. So if HA is weak, and it is, again, we're going to take that concentration of HA initial over the Ka. It's going to be greater than 100. It's going to be okay. That's part of our assumption when we're doing our shortcut. But it is. We're using weak acids. What can I do? What can I do? Oh, we're just getting towards the test. Don't lose it now. We've worked so hard to get here. We've done it over and over again. What can I do? The approximation is good. Yeah, Jesse? Which ones can I get rid of? I can get rid of the one on the bottom because my HA is going to be big. Yep. Sorry? I can also get rid of this guy as well because by the same logic, this is going to be a tiny little number compared to my initial A. I can't get rid of that because then it's all 0 and it falls to pieces, right? Okay. So what do I have? I've got Ka equals X, and then I've got A minus initial, and then I've got HA initial. And if I ultimately want to get H3O plus, I need the X, so I'm going to bring everything to the other side. Ka times the concentration of HA initial over the concentration of A minus initial equals X. and X is H3O plus. Let me rewrite this. H3O plus. For a buffer solution is going to be the Ka, the concentration of the weak acid, notice I've now wrote weak acid, over the concentration of its conjugate base, initial. I just put the words in there so that we don't get messed up with what the A minus is. The A minus is the conjugate base. All right? There is the shortcut. We can call this, if you want to give it a name, the buffer equation. Now, I'm all out of space, but if I were to do this for a base, and I'm going to put it on the board so those of you who are listening to the movie, you can figure it out. If I'm dealing with a base, B plus H3O plus, H2O plus, that's going to get me OH minus and HB plus. So this would be for a base conjugate acid, all right, base conjugate acid pair where the Kb is bigger than its Ka. It's better at being a base. What's my OH minus concentration going to be if we carry the logic through? Everything's going to work out exactly the same. Except down here I'm going to have B, and up there I'm going to have HB. What's it going to be? What's it going to be? H3O plus. Substitute it in, do the logic. Yep, Jesse? Kb, the weak base over the conjugate acid. And that's initial. And that's going to be the OH minus for a buffer that is a base and its conjugate acid, where that thing's better at being a base. Well, that's not too tough. All we've got to do now is, when we get finished all this, organize all of our equations, and if you can keep all those equations in mind, then you're in good shape. Let's use these equations now. So, at this point, I'm saying, instead of it being just a solution of HF, it's a solution of HF with some sodium fluoride. Now, if I didn't give you this equation, you'd have to check out the Ka for HF and the Kb for F minus, and you're going to find that the Ka is bigger than the Kb. That means it's going to behave as an acid conjugate base buffer. There is the equation representing that acid conjugate base buffer. And I guess if we really wanted to, we could write some information underneath. We haven't done this in a while, but we could do this. 0.2 moles of HF in 1 liter means that there's going to be 0.20 mole per liter. And here I also have 0.2 moles of NaF. And therefore, I'm going to have 0.20 molar F minus. There's my concentration of my acid. There's my concentration of my base. Conjugate base. What's the equation we just came up with? H3O plus is equal to. I need you to tell me, because I don't remember. I haven't memorized it yet. Jesse? Ka. Weak acid initial divided by conjugate base initial. Now, there's a special case here, and this is true for most buffer solutions. What's true about the concentration of my weak acid and the conjugate base in this scenario? Yep. Therefore, what's going to happen to my equation? It's just Ka, it'll cancel out. This will happen more often than you think. So let's write down this special case. If concentration of weak acid initial, well, it doesn't even have to be initial. It can be anywhere in the buffer, is equal to the concentration of the conjugate base, then H3O plus is simply equal to the Ka. That's a shorter shortcut. Wow. So if I have a buffer, whether it's acid conjugate base, base conjugate acid, and I start with the same concentration of the acid and conjugate base, then the H3O plus is simply going to be the Ka. What is it for this particular situation? H3O plus is equal to, we just had it a moment ago, I'll need it back, 3.5 times 10 to the negative 4, and therefore pH is equal to got a value? 3.50. Just two significant digits. 3.46. Sorry, three significant digits. I apologize. 3.46. To two decimals, I want it. To two decimals. 3.46. All right? That's a little higher of a pH, closer to 7 than it was when it was pure. But that makes good sense. We've added a little bit of base. That's going to bring it a little higher. All right? So that's how we calculate the the pH of a buffer solution. This pH would be when we have a nice buffer of equal concentration of acid and conjugate base. That's how we calculate it. Now let's apply some stress to this buffer, because all I've done now at this point is made the buffer. Take some of the acid, take an equal amount of the conjugate base, cancel them out. I've made the buffer. This buffer is now ready to do some buffering. What's it going to buffer? Well, it's going to buffer the pH. This buffer is poised to control the pH around this 3.46. Now let's dump some strong acid into it and see how it reacts. See what the effect is on the pH. And so now we want to stress the buffer. We want to add some acid or base to it. So we're stressing the buffer. It needs its own slide. It's that exciting. We're going to stress the buffer. So stressing the buffer is simply adding some strong acid or base to the buffer that we have. For the sake of mathematical simplicity, we're simply going to add 0.1 mole right into the liter. However we do that, don't worry about it. We would actually change the volume slightly, but we're going to not worry about that in this course. And let's figure out what it does to the pH. Again, this is an HF, H2O, H3O plus F minus buffer. Because the Ka for the HF is bigger than the Kb. It's an acid conjugate base buffer. Let's write down what our buffer contained before we stressed it. 0.20 mole per liter, and it came from moles in 1 liter, and 0.20 moles of the base. And now I'm going to add some acid, some strong acid. Which of my two chemicals is going to leap into action and save the day? If some acid from HCl, strong acid, is added to a mixture of a weak acid, HF, and a conjugate base, which of those two entities is going to leap in and save the day and mop up all of this H3O plus that's going to be added? Which of those two entities is going to react? Yep. Why is that? And it can grab up the H's. So when a strong acid is added, the base will be converted into acid molecules. And I'm going to just put that off to the side. The strong acid will convert F minus over to HF molecules. That means my 0.20 that was HF is now going to get smaller because it's being turned into, sorry, that was F minus is now going to be turned into HF. How much smaller is it going to get? Sorry? Twice as smaller. Can you say twice as smaller? That's a great term. That's hilarious. It's half as big. Why is it going to get half as big in this case? It's not going to get half as big in every case, but in this case, you're right. It is going to get half as big. Why is it going to get smaller by half? Yep. There's 0.1 molar of the acid. The 0.1 molar of the acid is going to take away 0.1 molar minus 0.10. That's going to leave me with 0.10 molar of the conjugate base left. What's going to happen to the HF concentration? Yep. It'll go up by 0.10. Yep, and that's because it's been converted into it. Plus 0.10. There's been a shift. I don't normally write it this way, but you can say here 0.10 has moved from there to there. That's essentially what happens. Let's now determine the pH. Oh, by the way, this is 0.30. So now, H3O plus is still going to be the Ka, and what is it, the weak acid over conjugate base? I can't remember again. Yes. This is the weak acid over conjugate base. They're not the same anymore. I can't cancel them this time. It's not our special case. But I do know what the numbers are. I should know this Ka by now. You've told it to me 100 times. Sorry? 3.5 times 10 to the negative 4. The weak acid is now 0.30 and over 0.10. And that's the H3O plus. And very quickly, you can get the pH, like we know how. For some reason, students fear buffers, but the mathematics is easy. we simply use the buffer equation, and all we got to do is figure out how much weak acid and conjugate base there is and put it in the equation, and you've got it. What do I have for H3O plus and then pH? Mike, what do you got? Well, give me the pH if that's all you've got.
2.98.
98. We like that? All right. Just to illustrate, delta pH. What was the pH before we added that strong acid? What was it in the last calculation? 3.46. So final, delta is final minus initial, 2.98 minus 3.46. How much did the pH change when we added that 0.1 molar HCl? Just a subtraction there. Somebody got that subtraction? Yep.
Drop by
0.48 pH units. I don't have room on the board right now, but I'm going to do it on the chalkboard. If I simply put HCl 0.1 molar right into pure water and it became all H3O plus and Cl minus, in other words, I had 0.10 H3O plus because it's strong. What's the pH of that? What's the negative log of 0.10? 1. If I added HCl to pure water, its pH would have went from 7 down to 1. That's a delta pH of -6. If I added just pure HCl into water, its pH change would drop by 6 units. But because of this buffer, its pH change was only 0.48. That's a buffer. Now, its pH started out lower, but for certain biological systems that need pHs that are in the 3.46 range, then that's going to be a good group of chemicals to have. Evolution would have taken care of that. Let's now add some base. Base is simply going to have the opposite effect. It's going to take some of the H's from the weak acid and convert them into the conjugate base. All we're going to do is shift some ions over in my buffer. I'm going to do the same calculation. I'm going to get a very straightforward thing. Now, I've changed the number just to change it up a little bit. Write yourself a little equilibrium equation. Put your concentration of HF and F and shift some over. I'm hoping if you've start writing the question now, I'm hoping you've already started the process. Again, this is an HF H3O plus F minus buffer. It's an acid conjugate base buffer. I started with 0.20 molar, 0.20 molar. This time I'm adding 0.15 moles of base. Who's the hero this time? Which entity of my buffer is the hero? HF. Excellent. HF saves the day. Steps in, donates its F. H's. It's H's. Which means my 0.15 heads that way as it donates those. All right? A little note on the side. Strong, and that's a scribble. Base converts the weak acid to base. HF becomes F minus. That's going to be true for any buffer, whether I'm dealing with a base conjugate acid buffer, which we'll do an example in a moment. That's always true. If you add a base, the acid steps up and saves the day, converts it over to base, which means 0.20 minus 0.15, what is that? 0.05 molarity, and 0.20 plus 0.15, and that's 0.35 molarity. And then the equilibrium runs. We use our shortcut. We get our H3O plus, and it becomes very repetitive. H3O plus, Ka, weak acid over conjugate base. And again, I need to ask that number one more time. 3.5 times 10 to the minus 4. Oh, I don't need to ask it. 3.5 times 10 to the minus 4. And now I've got 0.05 over 0.35. And again, you can go right to pH on that guy. Do we have a value? I'll take pH, H3O plus, I don't care, Caitlin. 4.3 something, 4.30. And again, it isn't asked here. I do have a question that asks, calculate the change in pH. What is the delta pH from our starting point? 4.30 minus 3.46? 3.46. And what did it change by? Caitlin's looking at a number. What do you got? 0.84. A little bit larger of a change this time, but we added a little more base. All right? Okay. So I've got a couple more examples to do, but I want to finish this movie off. Man, my poor computer's probably choking. It's been recording for like 45 minutes. Let me just jump ahead to a slide that I do want to just talk about at this point in time. All right, we'll come back to that. Buffer capacity. You can write that down now, and then we'll go back to the other problem. As you might hopefully start to realize as you are doing those last two problems, that my buffer would run out if I added any more than 0.2 mole. And that's because all of the acid or conjugate base, weak acid, conjugate base, would be used up. And then the buffer's pH again would change drastically. It would be like adding it then to pure water. And the pH would start to take off in whatever direction you've added, right? If you've added base, it's going to head up. And if you're adding acid, it's going to head down drastically. So there is a limit to the amount of strong acid and base that a buffer can handle. It's determined by the concentration of the conjugate acid-base pair. So as you're writing here, I'm going to just orally, put down a summary here up for the movie since it's still running. We have just written down a shortcut equation for buffer calculations. We've used it 2 or 3 times. A buffer is typically made up of equal concentrations of the weak acid and the conjugate base, or vice versa. If they're at equal concentrations, they cancel out of the equation, and the H3O plus then becomes equal to the Ka. That's your initial buffer pH. And that's a handy thing. That means you can actually go to a table of Kas and you can pick out the proper acid-base combination that will give you the right pH starting point that you want. That's a handy way of looking at it. Once we add a strong acid or base, that shifts the concentrations, and that means we cannot cancel those values anymore, and we simply put them in the equation. All right, let me stop this and we'll get back to